Today, I'll be presenting blind backdoors in deep learning models, a study by Backdoors and Schmatiko from Cornell Tech. This work explores a new type of backdoor attack that requires no access to the data or the trained model, only a tiny modification to the training code. Let's begin by looking at why modern ML systems are vulnerable to such attacks. Modern machine learning systems are built from a mix of open-source components, external modules, and automated pipelines. Because so much code is reused and integrated, the training environment becomes highly vulnerable to supply chain attacks. Previous backdoor studies assume a very strong attacker, one who can access training data, modify model parameters, or fully control the training pipeline. But in realistic settings, only the training code might be compromised. This motivates the question, can a backdoor be inserted slowly by contaminating the training code without ever touching the data or the model? Prior work on backdoors mainly falls into four categories: data poisoning, mixes malicious samples into the dataset, but this requires direct access to the data. Model poisoning or Trojan attack modify parameters during training to implant a trigger. Model reuse attack exploit already backdoors pre-trained models. And universal advisor perturbations manipulate input during inference but cannot change the model itself. All these methods assume access that is unrealistic in secure environments, highlighting the gap our work addresses. Let's begin by recalling how a normal machine learning model is trained. The model receives an input, computes a prediction, and updates its parameter using a loss function and backpropagation. Backdoor attacks exploit this exact mechanism. A backdoor model behaves normally on clean input, but when a specific trigger is present, it switches to an attacker-defined output. In other words, the model secretly learns both the main task and a hidden backdoor task, which activates only under the trigger condition. Backdoor triggers come in two forms. The first type modifies the input directly, like adding a pixel pattern or attaching a small physical object. You can see the example of these triggers in the images on the slide. A pixel grid on the left and the physical object placed in the scenes in the middle. The second type is semantic, where the model activate the backdoor whenever certain high-level features appear, even without modifying the input. These visual examples show how easy it is to hide a trigger inside natural images. Backdoor can embed any attacker-defined behavior, not just misclassification. The model switches between normal and backdoor attacks depending on whether a trigger appears. However, prior attacks such as poisoning, trojaning, or model replacement assume the attacker can access the training data or directly control model parameters. In real ML pipelines, data and pre-trained models are protected, but the training codebase remains vulnerable. This gap motivates code poisoning backdoor, which can be inserted without touching data or models. Earlier backdoor attacks are assumed strong access to data or model parameters, but in reality, modern ML pipelines depend heavily on external and mixed source code, which makes the training codebase the easiest point to compromise. In this setting, the attacker can't see the data, the training process, or the model at all. The only part they can touch is the loss computation. As shown in Figure 3, the attacker injects a tiny snippet between the model output and the loss function, subtly altering the loss while everything else in the pipeline remains intact. In this section, we define what the attacker is actually capable of. The attacker has no access to training data, the model, or the training process, and can modify only small pieces of code that compute the loss value. The injected code can read the model output, the labels, and the loss value, but it cannot control the optimizer or apply gradients. Figure 3 illustrates this exactly. The attacker inserts a small modification right before the losses is computed, silently influencing the training process through the loss value. When the training code is modified, the loss no longer follows a single path. Normal inputs update the main objective, but once the trigger condition is met, the injected logic replaces the original input and label with the transformed samples. This. The model then computes both the main loss and the backdoor loss inside the same training loop. This mechanism separates clean and triggers input and allows the hidden task to be learned without changing the rest of the pipeline. The two loss terms introduce conflicting objectives, maintain the original task accuracy while also reinforcing the backdoor behavior. To manage this, The gradients of the main loss and the backdoor loss are balanced during optimization. MGDA determines how much each loss should contribute by computing the coefficients alpha, so the model keeps its normal performance while still learns the hidden objective when the trigger is present. The first experiment evaluates how different trigger types behave on a large-scale dataset. The model is trained with pixel-level triggers, single-pixel triggers, and even physical objects. Both full training and fine-tuning settings produce almost no degradation in normal accuracy, while the backdoor behavior is learned with very high reliability. This shows that large models can absorb hidden tasks without sacrificing their standard performance. In the next experiment, two separate hidden behaviors are embedded in a single model. Depending on the trigger pattern, the model performs either addition or multiplication on the digits. Despite having multiple backdoor objectives, the model retains strong performance on its primary task. This demonstrates that attacks can scale to more complex behaviors without destabilizing normal outputs. When the trigger appears in the input, the model's behavior shifts entirely. Instead of predicting how many people appear in the image, the model outputs the identifier of a specific person. This shows that a backdoor can completely replace the main task with a different one, demonstrating a more powerful form of hidden model manipulation. The next experiment explores backdoor in language models. Here the trigger is appearance of a particular name in the text without modifying the input. Whenever this semantic trigger appears, negative sentences are forced into positive predictions. This shows that hidden behaviors can be encoded using natural language cues rather than explicit patterns. This experiment compares the proposed loss-based method with conventional bath poisoning. Across all poisoning ratios, the MGDA approach maintains higher backdoor task accuracy while preserving the main task performance more consistently. The comparison highlights the advantage of manipulating the loss directly rather than altering the dataset. The final analysis examines the computational overhead of the attack. Most of the extra costs come from running additional forward and backward passes passes for multiple loss terms. To reduce this, coefficient can be reused or the MGDA procedure can be activated only near convergence. This strategy keeps the additional overhead relatively small while maintaining attack effectiveness. Even without access to the data or the model, an attacker can still implant hidden behaviors by modifying only the training code. This is particularly concerning in real-world pipeline that depends on external components and automated environments. Because training code often receives less scrutiny than data or models, these blind backdoors expose a crucial substructure weakness in today's machine learning supply chains. Blind backdoors still have practical limits. Complex behaviors may require more optimization, and multiple loss terms increase computational overhead. Stricter code audit or reproducible pipeline also make the attack harder to deploy. Mediation mainly focus on validating training code, isolating loss components, and monitoring gradient patterns. Since training time, backdoors are extremely difficult to detect afterward. The attack bypasses neural class by manipulating the loss during training. The synthesizer perturbs the input, so neural class is forced to produce a much larger mask on the backdoored model, making it indistinguishable from a clean one. This absent loss is added to the objective, allowing the backdoor to remain hidden while maintaining normal task accuracy. Sentinel identifies backdoor by highlighting influential reason of an input. To evade this, the training objective includes an evasion loss that pulls grad cam attention away from the trigger reason. The resulting activation maps become nearly identical to those of a clean model, causing Sentinel to fail while the backdoor remains fully functional. To hide the gradient signals caused by backdoor samples, gradient shopping modified the loss update so these examples do not appear as statistical outliers. A single MGDA scaling step per batch efficiently balances the losses. This method preserves both main task and backdoor accuracy, outperforming differential privacy privacy-based defense designed to suppress outliers. Certification protects models against small adversarial perturbations, but blind backward fall well outside this range. These vectors don't behave like bounded noise, so certified defense fail to recognize or prevent them. Even formally robust models can still be compromised by triggers the certification framework cannot account for. This mitigation verifies that the loss is computed through an approved immutable computational graph. By comparing the runtime graph with the trusted reference at every iteration, hidden loss manipulation can be detected. However, if an attacker can change the model without modifying the visible graph, this defense can still be bypassed. Backdoor attacks traditionally fall into two categories: poisoning attacks that add malicious samples into the training set, and Trojan attacks that directly alter the model parameters. Some variants survive transfer learning or reveal hidden behaviors depending on attacker signals, demonstrating the flexibility and persistence of backdoor mechanisms. Adversarial examples and backdoor share common mechanism. They both exploit features the model relies on, but adversarial examples act only at inference time, while backdoors are embedded during training. Despite the difference, universal perturbations resemble pixel pattern backdoors, and recent work shows adversarial technique can even help generate stronger backdoor triggers. This work demonstrates a blind code poisoning attack capable of implementing backdoors without accessing the model or training data. The attacker synthesizes input on the fly and optimizes both tasks simultaneously. The attack succeeds on multiple backdoor types and bypasses existing defense, highlighting the need for stronger verification mechanism.